some oh, my alarm. We have to wake up now. Okay, let's see. Let's try to start with some general things. How to do here? Zoom participants more. Okay, I don't know here what's going on, but let me see if there is some new thing I have to say. Maybe about Canvas first. Okay, I think that many of you have already sent me a message about the groups, and so I've been able to place most of you in groups. That's very good. And so later when we go to the lab, we have only a group from 1 to 7, as I sent you in message, and then the other group from 8 to 11, if I remember correctly, will come later on. I think 1:30. The second batch of groups, so from 8 to 11, will have to wait in D386. So whenever you arrive, you wait in D386, which is the room that is near the D381 where we are working. And whenever one group go out, then I will then call you in, or eventually I can also give you maybe the breadboard and the components, so you can even start on the 386 to at least build the breadboard. So then you can come in the 381 whenever you need to connect the device with the instruments. Yes, so try to get in again 1 meter distance, group by person by person, when you get into the 381. And yeah, once you get sit, then try to stay sit, of course, on your place. Whenever each person will come, I will tell the person where you should sit. Hopefully I will have time to place for you all the instruments before you come, because probably I will finish then the undervisning hour maybe 15 minutes before, so I can go in the lab and then place all the instruments, and then when you arrive is everything there. And yeah, I think that's it. I don't know if you have seen, but I uploaded the links of the lectures for the lecture of the digital circuits. So the lectures that we did yesterday and the lecture that we did last week, Thursday, you can find it. Let's see, Canvas here. You can find it here in Canvas. So you click here, Forelesning Notator, and then the V, this link with the V is the video that I create an extra video, maybe giving more information about the content of the lecture. And these two link here with F, these are instead of Forelesning, so the lecture that we did actually in class. So if you click there, then there is Ole provided me the link where he saved the lecture, the recording of the lecture. So if you just click here, then you will be addressed to the video. Okay, so today, if you notice, I'm very slow. I think it should be forbidden to wake up so early. So I'm still quite sleepy. So yeah, and yes, I will definitely share the PDF for the lecture. The one for the lecture of the digital circuit is already shared. So again, is in the same place where I just showed in Forelesning Notater. There is already all the lecture for the digital part. For the lecture of today, I will share it maybe today. I haven't finished it, the second part, which we have to finish, I think, on Thursday. So that's why I didn't upload it in the end, but I can maybe upload the part that we did today. Most of the slides, they are the same that I did last year. So if you look about last year, then it's more or less the same. But anyway, we will try to go through today. So today will be hopefully something, a lecture, maybe most on my pad, and I try to synchronize it. It seems it works. So then we'll try to do exercise about electric circuit. If my mind is sufficiently awake, then hopefully I will not perform any mistake. But yes, so today is mainly about electric circuit theory. I think I don't have any information related to Canvas. If you have any question about it or the lab later on, please then ask now. Otherwise, I will start with the lecture. So yeah, you can ask both in chat and both with your microphone. Okay, seems okay. So if yeah, it's already 17, so we start. Okay, so welcome everybody. This is the lecture number 3, electric circuit theory. We are going to review the basic concepts, but that you have already, of course, seen in ELELC, but I will go also through the same concept, but from an electronic point of view. So I will try to give you an electronic view of what you have done. So it will not just be a repetition, maybe an interpretation of the formulas and the physical phenomena that have you studied. Because again, as electronic engineer, a bunch of formula itself, they don't mean anything to us. We have to try to interpret them. So give them a physical meaning. When we know that, then we know how to use them. Otherwise, it just could be a mathematician job. So we need to understand what we're doing. Okay, let's start. Let me see how to change. Okay. So as I said, we're going to study electric concepts from electronic point of view. And this lecture is not meant to explain in detail or give you the basic about the electric circuit. I assume that you already know this concept very well from Elektriske. I'm going to repeat some of the concept, but I'm not going in detail. So I'm just, as I said, give you an interpretation. So if you do not know them, you have to look on yourself on the book of Elektriske ELELC. Is another thing that is very important in this kind of introduction and motivation of this lecture is that I'm not going to use the 3 phases theory that you study in Elektriske because this is not the job of, is not a topic that electronic engineer deal. Electronic engineer usually design very small devices, portable, which have low voltage, low power, and work in general with small signals, you understand? So we are talking about currents of microvolt, millivolt, current of milliampere, microampere, nanoampere, even picoampere sometimes, and voltage signal around voltage, volt, millivolt, and microvolt. Instead, who actually use this concept about 3 phases are those ones that are called electrical engineers. Maybe the students from Elauto, they use it a little more than us. So they work with higher voltage and higher power than us. Electrical engineer can even work with kilowatt and kilovolt, and there were actually 3 phases system they are used. So in this case, in this course, we don't go to use 3 phases circuit. So this is kind of like show you more or less how your life will be different than electrical engineer. Most of them, they work with electric grid system or high power system. They are kind of like always, or many times they go to the place where this power system is built or is operating. So they have to do some check about the electric grid or the electric system there. In our case, as electronic, most of the time we will be in our lab. I mean, you will be in your lab, in your company, hopefully, and you will work on a lab table, and you will be more chill because you sit on a table and then just do some test on PCB or some design on your computer. So it will be more an office, let's say, work and the electronic engineer. Um, I have to emphasize that there are two types of electronic engineers. This one I think is better you know it now. Um, the one that is called PCB printed circuit board designer, and the other one is called ASIC designer, application specific integrated circuit. It's good to know because many of you may have questions, so I want to just answer to all the probably the question about maybe your job, future job that you can do in this lecture. The PCB designer is an engineer that design circuit on PCB, printed circuit board. So this one green here is the printed circuit board, and so only the green cord here is the PCB. Then you mount all the components over the PCB, and like for example here there is a capacitor, a diode, this is a MOSFET, this is an integrated circuit. So all of these components like capacitor, diode, and MOSFET, which contain just one component inside the package, are called discrete components. So this object here, which we know is a capacitor, it actually contains inside one electrical capacitor. So this is just the package of the capacitor. Inside the package, there is the actual capacitor. Like this one is just the package of the diode. Maybe I should put the pointer so you can see better. So this is just the package of the diode. Inside there is the real diode. And this is just the package of the MOSFET. So inside there is the real MOSFET. But there is still one component in these three objects that I indicated. Therefore, they're called discrete components. Instead, if there are more electrical components inside one package, it's called integrated circuit, like this one. In our case, you know, we will work with CD4007. That is an integrated circuit because there are 3 PMOS and 3 NMOS inside. Yeah. So this is practically the result, the task we are doing in this course. So you will become, I will give you knowledge to design this kind of device circuit. What about ASIC designer? ASIC designer instead design microelectronic circuit, which actually should be, in some way, if you think the topic of this course, because this course is called microelectronics. Unfortunately, I don't know why this course is called microelectronics. It was actually a choice of the previous teachers or responsible. We will not go much micro things in this course. Again, because this is all of these components, they are everything except micro. So you can touch with your hand. So it's not micro. I mean, there are some components that are very small and can be kind of like around 1 millimeter or 0.8 millimeter, yes. But again, when we talk about micro, we talk about 10 micro, 2 micro, something like that. And here there will be nothing that is 1 micro, 2 micro. No component can be 1 micro, 2 micro, because otherwise you cannot actually place it with your hand, or it's difficult to place with any tools. But this ASIC designer instead design microelectronic circuits, which means circuit which are in the micro scale. So micro, 1 micro, 10 micro, and so on, even less. So it practically design what is inside this package here, this integrated circuit here. Because of course, as I told you, there are 3 PMOS and 3 NMOS, but how do you build the actual 3 PMOS and 3 NMOS? Or how do you design the circuit inside of this integrated circuit here? And this is the task of an ASIC designer. So you understand that to build something very, very small, the cost of the device it increase. So if you wanna create a prototype of a microelectronic circuit, so something inside here, of course it costs more because you need the fabrication process much more expensive. Um, and so from this point of view, being an engineer of PCB is much easier because the cost of a PCB is much smaller than the cost of a microelectronic circuit. This ASIC, so the circuit that is inside of this integrated circuit, in order to design it, require a very deep understanding of MOSFET, transistors, and semiconductor physics. We are going to touch a little about these things. Again, we start already to understand what is a MOSFET, transistors, but more knowledge must be acquired. This one is just a course that give you a little hint. In our master degree at Micro Nanosystem department, we have another course which is called Sensor Interfaces, which will give you actually more knowledge about this ASIC design. So that is a course about ASIC design. Okay, so I want to give you just a view about what is inside of an integrated circuit, like inside of here, because maybe you can be curious about what could be the next step after PCB designer. So what actually an ASIC designer do. This is a component, has CD4007, but it has more pin, and it is a little smaller. You can see it can fit in the tip of one finger. And let's, for example, try to cut off here the package. So let's say that I know one method to remove the top part of this package. The package is this black part. So if I'm able to remove this top part from the components, you will see something like that. So I think this one should be a topic actually that Christine or Vu should go through, but I'm not sure. I don't think they actually go too much in detail about it, but it's very important. So you can understand that this is the real integrated circuit or chip made in silicon that is inside of the package, this integrated circuit. So this is the real part, actually, the ASIC designer design. This is a microelectronic circuit. This microelectronic circuit is then connected to the package by bonding wires. And this pin here, they are then connected to the pin here. So this pin here is connected to that. This pad, this is called pad, is connected to the pin. This pad is connected to the pin. This pad is connected to the pin. And this pad here is connected then to the microelectronic circuit with a wire bonding. And here there is another micro pad, which then is connected here to the circuitry. Inside of this part, there are millions of MOSFETs. And so there are many MOSFETs. So this is thanks to the new technology available today. So I think it is interesting for you to know what actually is inside this package, because if in the future you like this field, you are going maybe to design these microelectronic circuits. Okay, and so the design is much more complicated. You have to learn, first of all, how to design PCB, then you can become maybe in the future an ASIC designer. This course, again, will focus only on PCB design. Okay, so let's start with basic electric components very fast. We're going to look about the packaging very fast of these components, which again, I hope that Christine should have done this, or Vu, but I don't think they do these things. I don't know why, but then we're going to, I will explain you what is THD components, SMD components. We will focus mainly on THD. We will look about constitutive equation, and then we are starting to do something electrical. And I will pass to my pad, to my tablet. Okay, very briefly, this is the three components that you, okay, if you have any question, of course, feel free to ask, write in the chat or speak out the microphone, feel free to ask. These three components, they are the basic electrical components that you have seen in ELALC, inductor, spoler, resistor, mustander, and capacitor, condensator. Okay, I get my alarm. There it is. Okay, and these three components, and you may have worked already with that, with these real components in the lab in LALC, are discrete components. So for example, this one, this components here is a resistor, as maybe you know, and of course is a discrete component because inside of this package here, there is only one electrical resistor. So again, discrete components means that inside of this package, inside of the package of the component, there is only one electrical component. Okay. So there are two types of discrete components. One is called THD, the other is called SMD. THD means through hole device, and SMD means surface mounted device. The THD requires that you do some hole in the printed circuit board, while the SMD can be placed directly on the printed circuit board. What does it mean? This is the, for example, this is a resistor, which is THD, which means, as you can see, there are some hole in the printed circuit board, and this is the same that is represented here, the cross section. So you have to fit the component inside of this hole, and then you solder this component here, where is the copper part. And then the component is fixed and connect to the PCB. This is called through hole device. You understand it's quite intuitive because it has to go through the hole. Instead, this is the SMD resistor. It's still a resistor. As you can see, this is a SMD resistor. It's still a resistor, but the package is different. It's much smaller. You can see it can be almost not visible on a tip of a finger, and it will be just mounted over the surface of the PCB. So you just place on the PCB, and then you solder at the side, in this side and this side. So you don't need a hole. Uh, and actually, you're going to work with this. So be ready that you're going to work with something pretty small. Yeah. Okay, this is mainly about the package. It's important that you know what is the THD and SMD components. In your project, you will use them both. So actually, you will use more SMD, but in the other labs, so also you will use THD. So when I say THD, it may sound as a disease, but think about THD is a type of components, which is through-hole device. But SMD is surface-mounted device. Okay, so let's go a little more about packaging. This is a resistor, which is the THD components. You know that there are colors. Colors means they are related to the values of the resistor. I definitely encourage you to know these color things. There are actually resistors of different type. There are resistors that have 6 line here, other 5, other 4, other 3. So you should be able to read this kind of color. In my opinion, it's not mandatory, and I just encourage you to know it, because whenever you're in the lab and you search resistor, and sometimes you're in a hurry, it would be very fast to actually look about the colors and then immediately understand what kind of resistor it is. Personally, I don't remember all the color. I just remember the black, the orange, the red, and the gold if there is a gold line. Why? Because they are very common. If you have a gold line, it means that the tolerance of the resistance is 5%, which means that if you go to pick a resistor of 100 ohm, when you really measure it, okay, it can be 995 or 105 ohm, okay? So if you go to pick a resistor in one box in the lab, and in the box is written 100, of course, will not be precisely 100, because the manufacturer cannot produce a precise 100 resistor. There is always one little error. And the last line on the resistor, it tell you how much is the tolerance of the value. So how much is this error, more or less, the maximum error. Whenever it's gold, which is the most common resistor that you have, is 5%. Again, so if you have 100 ohm resistor, so if you go to pick 100 ohm, when you go really to measure it with voltmeter, with ohm meter, then it can be 95 or 105. Yeah. Yes. So be aware about this. Of course, the smaller is the tolerance, the better it is for you, because it means that it's closer to the ideal value, right? Yeah, so gold usually is the most common, and then black is because means 0, red because means 2, and orange means 3. These are very common value. I don't remember, although also 1 is very common, I don't remember that is related to brown, and neither 4, yellow. But If you can remember, I definitely suggest you. Many times I'm in a hurry in the lab, and then I definitely have to go to take the ohmmeter, then measure it, and so on. But so it's a suggestion. There are different package for capacitance, as you can see, different technologies. There are ceramic capacitance, multi-layer capacitance, mica capacitance, electrolytic capacitance, and surface mounted, okay, ceramic capacitance. But there are different materials that can be used to build capacitors. There is a purpose, of course. Different material are better in different application. I'm not going here in detail, maybe in another lecture later on. Here is just to show you that you can see capacitance with different packages. The most dangerous of this is this one, electrolytic. If I have the possibility, I wanted to prepare this video. Actually, I want to do in class. I want to see something very dangerous, that actually this capacitance can explode. So I can actually, I wanted to show you how this capacitance explodes, not to create bomb to throw to your friends, but just to show you that it can be really dangerous. So we are not going to work much with this, because this one is used when you need very high value of capacitance. But if you will ever work with that, then be very, very, very careful. It happened to me. It exploded in front of me, and it's not a fun, nice feeling. Although fortunately, nothing happened. But it got me on surprise. So I was in high school, and was, I think, 16, and I have this lab activity, and if you mount it in the wrong direction, this will explode. Yeah. Anyway, let's continue. These are type of inductors or spooler, and you can find in different packages also here. So don't be aware if, don't be surprised if you see them in different way. The main concept here is just that you have a coil, a wire that is kind of like rotated as a coil, right? So this is just a copper wire which create a coil, and then you get your inductor. Depend on the number of turns of this coil, then you have a certain value of inductance. So in theory, in principle, you can build a coil on your own. Okay, so finally, let's look into the real part of this course. Let me see. Yeah. I will try to go here at the very beginning, then when is some more theoretical part, I will change it. Okay, so let's go to the next topic. Again, if you have a question, just stop me. If I'm going too fast, stop me. Curious question about something, just ask. I know you're probably sleepy like me, and so I understand if you don't have a question. Let's continue to the next topic, three constitutive equations. Constitutive equations are the most important formulas that you have to know and you have to remember from here and your end of your career as electronic engineer, which practically define the relation between the voltage and the current between resistor, capacitor, and inductance. I mainly remember them just because I work every day with them, so it kind of like become part of my library, but maybe for you would be a little difficult to remember, but it's just three formulas, so but very important. If you don't know them, then you will have very difficult to understand many things in this course. These are the three magic equations. As I said here, they are super mega important. So VL equal L DIL divided by the T. This is for the inductors. VR equal to R times IRT, which is the resistance, and for the capacitance, IC equals CDC. Again, I on purpose describe them like that because, as you may saw, or as you may understood, I just wrote a formula, which by itself does not mean anything. So we have to try to understand actually what does this formula means, right? Otherwise, it's just a formula and it just remains something like, okay, I don't know how to use it. But let's understand how to use this formula. Let's start from resistor first. But again, my main concern is that you understand the meaning of these three formulas, and we are going to see what physically, how physically, which physical meaning we can extract from this. Let's start from a resistor. The relation between the voltage and the current is given by the Ohm's law, as you know. VR is equal, so the voltage across the resistance at any time is equal to the resistance value times the current through the resistance at any value or at the same time. So with T, T here means a certain time, instant moment of time. Again, this formula is correct only if the current is going in this direction and the voltage is this polarity here. Because again, is the current going this direction, then it means that this point is a higher electric potential and this is lower electric potential. If the current in your circuit go in the other direction, this one, as it's written here, is not valid anymore, but you have to add minus sign here, okay? Yes, so the main important things here is that you know that the voltage and the current across a resistor are proportional. So this is something that you have to try to learn also how to use these formulas very fast, okay? So for example, if I tell you that you have one voltage over a resistance of 100 ohm, how much is the current over through the resistance? Most of you at this point will take the calculator. One thing I will do probably from the next year is I will not allow the calculator in the exam, because this is a course that you have to become an engineer, and an engineer use the calculator when necessary, but most of the time has to do the calculation in your mind. I mean, the most important thing that an engineer has to do is not calculate the precise value, is to have an order about the value that you're calculating. I will make an example, like if I have to calculate the current, okay, uh, I have a resistor of 3 ohm and I have a voltage of 10 volt. How much is the current through it? I can say 3.3, 3.3, right? The current could be 3 ampere point 33333. But it doesn't really make sense to say the 3333. I can say, okay, it's approximately 3 ampere, because this is actually what I want to know as engineer, is the order. Is just to have to know if it's ampere, milliampere, or microampere, okay? Now, in sums, you also have to understand also. Now, it's not that from now you are going to neglect all the digits after the comma, okay, after the point. You also have to start to learn how to discriminate when to stop, okay? Uh, it depends on the situation and how precise you want your measurement, okay? But again, doesn't make any sense that if I ask you how much is the current through a resistance of 3 ohm when I apply 10 ohm at 10 volt, you give me 3.3333333. Don't, for me, the billion of 3 that give me after the digit, the comma, does not bring any information to me. I would be very happy actually if you just tell me 3 ampere, for example, or 3.3. That would be sufficient, okay? So please, when also in the exercise, don't show me a billion of digits after the comma. It doesn't really make any sense. Okay, so this is very important for me. Also start to try to make calculation in your mind. So try to use your brain is the first calculator, because it happened many times. It happened also to me, and it's still happening to me. That maybe because I don't know, I'm sleepy, I'm distracted, or whatever. That sometimes when you push in the calculator, you push the wrong button, and then you trust the calculator because it's a calculator, and then you write in your Bleak or in your exam the wrong value, and then you say, oh, but it's the fault of the calculator. Yes, but you didn't think before what could be the estimated value that could come out, right? So it's your fault first that you didn't actually have an estimation of the result that you should have. The calculator should just give you the precise value whenever you need, but you always need to have an estimation first. Okay, it's very important to me, this point, so please take it into account. Let's go forward. It's important that also, if we go back to resistor, you know, any conductive material is a resistor. So this is something I will emphasize in this course. So if you take a wire, a cable, a copper wire, okay, although if you apply the voltage right across this, I mean, you can think that if you apply a voltage on one side of the cable, you expect to measure the same voltage on the other side, right? Because it's just a cable, right? Ideally, it's the same. But in theory, this cable is a conductor, and as a conductor, it has a certain electrical resistance. So any conducting material, even a cable, is a resistor. But in the case of the cable, it's a very, very small resistor. In the case of a real resistor, so a discrete component which include the encapsulated resistor, then the resistance will be a little higher, okay? But any conducting material is a resistor, okay? And I will show you also in this course that sometimes we have to model cable as a resistor to show that there are some phenomenon that if you do not do that, then you cannot understand, okay? So it's very important, this point also, that you remember. So in electriske Kretze, probably this point was not important, but in electronic, this is very important. Okay, so for the resistor, I think this is the most physical things that I have to tell you. We are going also to see about the physics about the resistance, how electron pass through the resistance and what happened, why there is this resistance from physical point of view. I will try to give you some insight when we talk about semiconductor physics. Probably you already have seen something in LELC, but I don't think you have talked about the random motion of the electrons and Brownian motion of the electrons. So we are going to talk about that, because that is the reason why we have noise in this electronic circuit. So I just spoil it. So spoiler alert, in many circuits, one of the reason of your noise is due to this bad guy, which are resistors, okay? And in that case, it's called thermal noise, but we will look about it in detail. And to understand that, you need to know the physics. So that's why this course requires physics concepts. Okay, so let's pass to the capacitance. Here, maybe it could be nice to have the pad, but I think this is, yeah, maybe I can then shift to the pad. If you have any question, feel free to ask while I'm shifting to the pad. So stop share. Here it will share screen. There. Can you confirm that you can see my, okay, I can see, okay. Great. Yeah, we all, it's a crazy time, this one. I really hate when we have at 8:15. Because I'm going very slow and you are also sleepy like me. So but, we have to deal with it. Okay, capacitance. So I hope that some of you maybe have maybe the slide on one side or whatever, but anyway, I will go through my notes, whatever is in the slide. So for how to remove these things here. Okay, so for the capacitance, so this is the symbol of the capacitance. We have two terminal. We have a voltage, which I call VC, and this is the current IC. Again, I should also put the T because the voltage and the current may change in different moment of time. I like to use the arrow, but I know that from LELC, maybe you use the plus and minus, is the same. But I will show you that for me is much more easier the arrow. I will show you how to use the Kirchhoff low voltage with the arrow, because this is what I use, and this I think is probably the best method for doing the things. But again, you're free to use the method that you want. So again, the formulas for the capacitance that relate voltage and current is IC dt is equal C dVc over dt, which itself doesn't mean anything, right? So where does it come from, this? Well, this one comes from to another equation that is maybe more familiar and maybe more understandable, which is the charge stored in the capacitance, which I indicate with Q, is equal C V dt, where V is the voltage across the capacitance. So you know that if you apply a certain voltage to the capacitance, then you start to accumulate charge on the capacitance. And the charge that is accumulated is proportional to the voltage. And the proportional constant is C, called capacitance. Now, if you let me write like this. If you derivate the left side and the right side of these formulas here, you will find the magic formulas IC, C, dVc over dt. So it's not easy. If you do not remember these formulas here, do not worry. Just remember the main formulas. QDT is equal CVC, which actually is pretty intuitive. And if you derive that, you get the relation between current and voltage. Because again, the derivative of the charge, the variation of charge in time is current, right? And this is charge and this is time. So variation charge in time is current. Yes, so it's also important the unit. Remember, the unit is very important. The unit is farad for the capacitance. I didn't go in through again to the unit of current and voltage. I hope that you know at least that one. This is ampere and this is volt. And for the resistance is ohm. But I definitely hope these things you already remember. Okay, so I want to discuss a little physical meaning with you about of these formulas. This is very important, and because if you know how to interpret this, then you can get many things. Okay, let's assume this situation here. Yeah, so I didn't introduce any source of voltage of current for the moment. This is an F, it look like a T, okay. I didn't introduce any source of how to make the symbol of voltage or current, but I hope that you can understand this simple circuit here. So this is a current source which create a constant current. I don't know, it's not very important about how much current. I call this current I0, okay? And this current source is creating a current, this come out, and then I connect to this current source a capacitance like this. So my question is, can you plot the voltage of the voltage over the capacitance? So can you tell me if you want to plot the voltage here, VC over T, what is the voltage that we have in this case? Any one of you, some guess? I definitely encourage you to give your opinion, regardless what it is, wrong or correct, but at least I know if you have an idea about these things. Whatever comes to your mind. You can also say sinusoidal signal, although there is not much relation in this case, but feel free to guess. What kind of yeah, okay, some one of you suggest it start from 0 and then it's going to the max. Yes, at this point I would say maybe ask what is the value of the max. But it's a good suggestion. But again, these capacitance can charge in different way. I mean, can charge like this, can charge like this, can charge like this, can charge like a line. So what is the actual way? Because in electronic is not whatever. What did I do? It become coconuts. Okay, it should be back now. Yes, okay. So in electronic, it's very important that you know actually what is the waveform, okay? So is it constant? Is it curvy or whatever? Okay, someone say nederste. No, but it is a good guess because again, what you have seen in ELK is that capacitance usually, capacitance usually charge in this way. I think this is what usually I've seen, right? And or maybe again, as someone said, maybe you can expect something like this or something like this. This is what you've seen. But this is because, again, this means that you did not actually understand the equation and the voltage relation between the current and voltage. And this is why I think this formula is very important. Because, again, you need to know what actually happened physically or what happened. You have to interpret the formulas. Otherwise, you always give this blind, this kind of answer, which derive just from someone that have told you that is like that, right? In this case, I may blame a little Jorgen because he should go in this detail. But I want to show you that actually it's not difficult. Every one of you can understand with your own ability what will happen. But you have to just be a little analytic, okay? So let's look about the formula here. But anyway, thank you for your guess. I definitely appreciate that you guess something rather than maybe not saying anything. Uh, Even in interview, when you find a job, remember that be silence is the worst things that you can do. You always have to talk because you show that you have an opinion. Otherwise, they think that you don't know anything or you don't have any opinion about that. Anyway, what will be in this case the voltage? Let's see. Okay, here in the top, as you can see, there is the formulas that relate the voltage and the current. So in this case, I know what is the current because it's the current source I0. I don't know how much is the actual value, but I know that this I0 is constant, right? I said before. And I want to know the voltage. Well, to find the voltage, I just have to do the inversion of these formulas here. And let's remind us the mathematic one concepts. So here, how do I find the voltage? How do I find the unknown voltage here? Well, I can, for example, first divide for C. So this one give me the derivative of the voltage here. And then the next step is just integrate in both sides, left and right. And this one give me the formulas that I want, which is integral of IC divided by C equal VC. In this case, VC dt. Okay. In this case, in the specific case, again, if you want to show me that actually is you understood, you don't need T because again, here at least for the current, because the current is constant, right? So for any time of instant of time, moment of time is always the same value. Okay, so how much is VC dt? Okay, then this is practically very easy. Okay, first of all, C is a constant, so we bring it out from the integral. So we write IC the T, sorry, I forgot here the T, 1 over C. Also here I forgot the T, and here I forgot the T. And yes, so I brought out the C from the integral, and this give me VC. Now, this one here is a constant. This one here is a constant. So what is the integral of a constant? So first of all, we just replace this IC with the value, the constant value, which we call it I0, right? This is the constant value. And so what is the integral of a constant? Well, here I hope that some of you know it, because the integral of a constant should not be difficult. The integral of a constant is just okay, let's show it also from mathematical point of view if someone doesn't remember. So this one is related to this part, which is the integral of C in the X is equal C times X, right? Where X is the variable. This is the mathematical things. In our case, our variable is the time, right? So it makes sense that the result of this integral is equal to 1 divided by C times I0 times T. This is equal VC dt. Okay? And now, this part here, what kind of plot has? How to represent this one in the left plot? Well, this one is a straight line, right? Because this is y, equal mx. So m is the constant part. Let me see here. This is huge. Let me do it smaller. Okay, this one is the, now it's small. There it is. So this one is the constant part. This one is my variable, and this one is what I want to find. So if I want to plot the voltage, this is nothing else than a straight line that increases, where the slope of the straight line is equal to I0, this is an F, I0 divided by C. So again, it's very important that you understand how to interpret the equation, because otherwise you don't know, you just give answer that someone already told you that it should be like that. And that's not the way that engineer do. That is what a technician do. So remember that, I mean, don't have anything against technician. They are very good estimation to a technician, but we have a different job. We are using our mind and our brain to understand what we don't know, to try to have expectation, to try to have a guess about what we don't know, based it on our knowledge. Instead, technician just repeat what the engineers say. But yes, the technician has easier task, because he just have to repeat like a parrot what the engineer said, but it's much more tough, because he has to go to the company every day, take this instrument, and maybe do the task. So it's maybe also boring, because you repeat all the time the same task. The engineer instead stay in the office, think about what he want. He can take a break, whatever, and drink a coffee, and then, but in a certain moment of time, he focus on the problem to guess something that is new. Okay, to solve something is new. Okay, so I think this is was very important things. We can take a break, and maybe in 10 minutes we start again. If you have any question, feel free to ask. Okay, I'll be back in 2 minutes, but the next topic will be charge inductor with constant voltage. So it derived from the same similar concept that we have done now. So try to think about it while I'm away. I'm away 2 minutes, and I'm back. Okay, I'm back. Okay, let's start. I'm going now to analyze a similar situation that we have done before for the capacitance. That one was just to show you that we need to know the meaning of formulas, and this is what we're going to do in this course. Every formulas we have to understand how to use it and what does it mean. I don't think there is no other thing. I could do also some other example with sinusoidal signal and other type of signal, but I think you understood now um, what is the procedure we are going to use in this course. If you have any question, feel free to ask, because I hope that is quite clear what I explained and why you should not rely on something that's always prove yourself everything. This is the work of an engineer also. We are always skeptics about everything. So be always critic and analytic in everything. If you learn how to do that, then you will become a good engineer. Let's continue then. What about inductors? Inductors is represented by this symbol. We have inductance L, then we have voltage, we have current IL, and as I said before, the main electrical characteristic equation, constitutive equation, is VL in T is equal L the EL T in the T. And again here, there are also something we have to understand how to interpret this this equation. We can try to do an exercise like what we did before. So we have one, so exercise. We have one, this time a constant voltage here applied to an inductor. And then here the constant voltage is V0. And we want to know how does it change the current in this inductor. Well, now you have already, I think, saw what happened before. It happened similar things. So it's very easy to prove that we start from the equation here. This one is the initial equation. What we want to find is IL, and the variable is VL. So we have to reverse the equation. So the final equation will be IL in T, 1 divided by L, integral of VL T in the T. I already reversed it. And so if, of course, the voltage here is V0 and is a constant voltage, what happens is that the result of this integral is equal to V0 divided by L times T. So this means that if we want to plot the current in time, then it means that the current increase in time. Yeah, correct. So yeah, I want to ask you also another things, which is still interpretation about these derivative formulas. Okay, so anyway, I hope that you understand better that how to use these formulas. So let's look about another things. Let's consider the capacitance, for example, which has the formulas IC, C, the VC in the T. What is the the sign of the current if the voltage in a certain moment is increasing? Okay, so I don't know, here we have, for example, a voltage which increase like this, always increase, right? And I want to ask you, okay, but in my capacitance I have positive current or negative current. What do you think is the value of the current? Is positive or negative? Anyone can guess? Yeah, well, if the voltage here you see in the plot increase, right? This means that the derivative is always positive, right? This is from a mathematical concept. This one is always positive. Capacitance is always positive, is a constant that is always positive, then this means that the current must be positive, okay? So, and if you have, on the other way, on the way around, on the other way, if you have a positive current that flow through a capacitance, you need to expect that the voltage increase, right? So if the current is, and now it doesn't really matter if it's constant or not, okay? But if the current through a capacitance is positive, and then this one is positive, right? I can rewrite this equation like this: IC divided by C equal dVC divided by dt. So we say this one is positive, this one is positive. So how will change the voltage? Well, we don't know precisely because we should know the current source. How does it change? But for sure, we know that will increase because the derivative is positive, right? So remember that this is another way to interpret also these formulas. On the other hand, if the current applied to capacitance is negative, then what happens is that this is here is negative, the capacitance value is positive, so a negative value divide a positive value then is equal to a negative value. So this one would be a negative value. But what does it mean that the derivative is negative? It means that the voltage will decrease, right? I hope that you know this kind of relation between derivative and slope of a curve. This is concept of mathematics 1. If you don't know, then review them because I don't have time to explain these basic concepts. As I wonder, again, this is what I'm showing you is a typical example of how this course will be intense because we are going to use all the concept about mathematics, physics, and electric circuits. Okay, I can repeat the same example for the inductance, but I won't do it because I think you understood. Let's continue. Okay, so in our electric circuit, we will use some symbols to draw the circuit. I don't know which kind of symbol you're using in electric Kretzer, but I will show you which symbols I use in this course, which more or less are the same, but there exist many ways to draw a symbol, for example, of a voltage source. Let's start from voltage source indeed, from sources. So sources. So we have, of course, voltage source, and we have also current source. For the voltage source, we have, of course, DC voltage source, which means constant, and AC voltage source, which usually you associate with a sinusoidal voltage source. The same for the current. So for the DC voltage source, you can use these two symbols, one like this, or this one here, as you prefer. For the AC, you can use something similar. Sometimes you use something like this. This is the most used symbol actually for AC. For the current is similar. So for the current, you can use this symbol here. Or you can use this symbol here. And for the AC, I like to use this symbol here. Yeah, pretty ugly. Like this. Correct. So the arrow doesn't mean much actually in this case because it's a sinusoidal signal, so the current go up and down. Some people, they also do like this, but again, it doesn't, is not a big deal. I just like to draw the arrow because at least it distinguishes from the symbol of the voltage. Okay, and there are other particular type of sources, which is, for example, the battery, which could be also considered as a constant voltage sources, but for the battery, there is a specific type of symbol. If you have only one battery, If you have only one battery, then the symbol is this one here. If you have two battery, it's very intuitive because it's just the symbol of one battery, one over the other, or you can just join them together like this. This is the symbol of two battery. So of course, if you put n battery one after the other one, you understand how this will become. So this is regarding the symbol that for the source that we are going to use. And now we are going to something a little more interesting than writing symbols. Okay, let's recall something about parallel and series. Okay, so when resistance are said parallel and when resistor are said in series. Two resistors are said in series if same current pass through the two resistor. This is the definition, okay? I will show you that you actually probably with the organ did not focus too much on this, and you will not be able to actually, as I showed before, to understand which will be series and parallel. But not for your fault, but just because I think, I'm not sure. But I think Elke should have given you a little more information, but let's see. Okay, but here you can see that the current, which I draw with the red arrow, is passing through both resistance. So this means that the resistance are in series, okay? So this one I write series. And two resistance are said to be in parallel when they have the same voltage across, okay? These R1, these R2. If I have that VR1 is equal to VR2, then they are in parallel. This is the definition. And you have to just think about the definition to understand if they are in parallel or series. Okay, so of course you can put, in this case, it's very easy to find the total resistance, the equivalent resistance. So this means that all of these two resistance behave like a big resistor, right? Which value, I call it equivalent resistance, which value is equal R1 plus R2. In the other case, the total resistance, which means that we can substitute these two parallel resistance with only one single resistance, right? Which have a value of R1 times R2 divided by R1 plus R2. Some of you have seen maybe in a LELC, you like to write it like 1 over R1 plus 1 over R2. Is the same. I like to use this one here on the left because it's much easier and faster. Product divided by sum. Okay, someone asked if it's matter how do you draw the resistor. Well, it doesn't matter. I mean, if you mean if I draw like this with many zigzag, or if I draw like this, it doesn't really matter how many zigzag you do. So if that was the question, then it doesn't really matter to me. We are always in hurry up as engineers, so we don't have time to take care about this stuff. But yes, but we will not do this. We will not do this here. This is actually the symbol of a bipole. This is called bipole because it has two terminals, one here and one here. And a bipole can be anything. Can be capacitance inside, can be a resistance inside, can be an inductance inside. You don't know because you actually do not remember, you don't represent what is inside. So that's why I don't like to use that. Some people use it because they always associate this rectangle to resistance, but I don't like it because in many contexts that is considered as a bipole, so it could be anything. And actually that will be the symbol that we will use to represent impedance. So that's why I don't want to use it as resistance, because otherwise you may confuse the two concepts. Okay, let's go through very fast. What happens if I have n resistance in series? So here, of course, I don't draw n, but I draw like this. Anyway, thank you for your questions. So if I have all of these resistance in series, because of course the current that pass through must be the same, I can replace all of this resistance with bigger resistance, of course, which value is equal to the sum of all the resistance, which can be written like this in short. We are going to use mathematical symbols if necessary, so be ready. And for the parallel, what happens if I have n parallel resistance? So draw it here. 1 or 2 or n. So I hope that that's some symbol. This one here does not surprise you. I hope that everyone know it. But if you don't know something that I'm writing, just stop me. Okay, this one again is equal to a resistor. Draw it like this, which is equivalent value is equal to 1 divided by 1 over R1 plus 1 over R2 plus plus 1 over Rn. This is the equivalent resistance of n resistors in parallel. Okay, but here I want to focus a little more on the parallel because it's very useful to have some tricks about the parallel. I want to ask you a question, and the question is, if I have 5 resistance in parallel with all the value of 1 kilo ohm, how much is the total resistance? And I cannot see you, so I don't know. But usually when I ask this question, I say, put down your calculator and do not use the calculator. I think some of you may have used, but so this is something that you don't need a calculator, and it's something that you should know how to do it as engineer very fast. Okay, that's correct. As Ole said, the value is just the value of the resistance divided of the number of the resistance of the resistors. So this means that if I have, I write here, if I have 5 resistance, how do I do this? I just draw it. Okay. If I have 5 resistance, all the resistance of 1 kilo ohm in parallel. What is the total resistance? You have to do the equivalent resistance is equal the value of each resistance, so 1K, divided by the number of the resistance you have, so 5. So this is 200 ohm. Okay. This is neither difficult to prove mathematically. It's very easy, of course. So this is a numerical example, but I want, again, as engineer, you need to know also why it come out like that, right? So take these formulas here on the top, right? We consider 5 resistance. So 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 plus 1 divided by R4 plus 1 divided by R5. As teacher, I have to prove everything I say. So all of these resistance, so we're assuming that all of the resistance are equal, right? Because I say that all the resistance were 1 kilo ohm. And I call all the resistance R. So this one become 1 divided by 1R multiplied for 5 times. I just write it all of it so you don't have any problem to see it. Okay, then the result is 1 divided by 5 times 1 divided by R, right? This guy here go up, and then it remain R divided by 5, where R is the resistance value, right? So yeah. Yeah, so this is why in general, okay, I can write it here. So in general, if you don't understand what I write, is normal because I write like a dog. But Just tell me, okay? If you don't understand, just let me know. So general, in general, parallel resistors with same value. So the formulas is equal R divided by N, where N is the number of resistance and R is the value of the resistance, okay? Is what just we did now. Okay, so I hope that this is clear. So let's do another example. Please answer it in the chat. It's just like a quiz, let's do like that. How much is the equivalent resistance of parallel resistors, all equals, of course, if each resistance is 10 kilo and you have 4 resistors. So what is the equivalent resistance of 4 resistance of 10 kilo? So put your answer to the yes, correct. Great, great, great. 10 points for Lillian, 10 points for Ivan, great. One thing that make me think to the answer of Ivan, of course, this is not great and whatever, but it's just a suggestion and just one my remark. Every times that you do give an answer, especially in the oblique, put also the unit in some way. I mean, the answer of Lillian is acceptable because it's 2.5 K, so I understand this 2.5 thousand, right? So every time you try to answer something, try to give also the part that, because 2.5 could be 2.5 ohm. Of course, in our case, I knew because I know the context, but again, it's always better to put, yeah, to put at least K. Because as you see, also I don't use to put ohm because I put the value close to the resistance symbol, right? So it's pretty obvious that is ohm. But to be precise and rigorous, then we have to write kilo, okay? But I accept also if you write just K or mega or whatever, okay? So ohm for me is not very, very important. But again, the more precise you are, the better it is, right? So that is, yeah. Okay, so let's pass. I think here I don't have to talk about anymore. I think you understand what we've done. What about capacitance? So let's look about capacitance. So capacitance in series, I do 2 capacitance here. Again, capacitance in series are those capacitance that also are characterized by the same current. Okay, if the current pass through, if the same capacitance pass through, sorry, if the same current pass through 2 different capacitance, then they are in series. Okay, what happened here? Okay, here. Okay, so this is C1 and this is C2. Sorry, my ugly C1 here. So the total capacitance here is equal to C equivalent, C1 times C2, C1 plus C2. Or again, as someone like it, like this. Again, you can already remember that the formulas for the capacitance is practically the opposite of the formulas for the resistance, right? So when they are actually in parallel, you have to sum them. When they are in series, instead, you have to just use that kind of formulas. Very complicated. Yeah, again, 2 capacitance are in parallel when they have the same voltage across. Okay. Yeah. So here I don't do any example because, you know, and it's the same of the resistance. So it seems quite trivial. Then there is the formulas for N capacitance in series and capacitance in parallel. Again, I don't go with these things. You will see in the slide, but I think it's pretty intuitive. I want to just go through very fast with inductance. 2 inductance in series, L1 and L2. The total equivalent inductance is equal to L1 plus L2. And if they have If they are in parallel, then you have the ugly formulas 1 divided by 1 L1 plus L2, or as I prefer, L1 times L2 divided by L1 plus L2. Yes, so these are the formulas. I wanted you to notice also one thing, and this is very important. I hope that Jorgen have said that again, but I want to emphasize this because it's a mistake I've seen. And if you do that mistake in the oblique, I will consider the oblique failed. And also, if you put this error in the exam, it will be failed the answer of the question, because it's a very important things. Whenever you calculate a parallel inductance or a parallel resistance, the value resulting cannot be greater than the two value that you made in parallel. It cannot be. So if you have in parallel 10K and 2.5K, now I don't know what will be the result, but for sure will not be greater than 2.5K, for sure. And if you write something greater, then that's a big mistake. It cannot be, okay? This come from the formulas, of course. Let me see if I can see. Where is it? Here. So if you analyze very well these formulas here, this is you will see that whatever number you put, the equivalent resistance cannot be greater. This is very, very, very important. I've seen students that put it bigger. I don't know. Again, probably because you use the calculator and you just trust blindly the calculator, and then you do a big mistake. And this just means that you don't actually think with your own mind. Yeah, correct. As Marianne say, it will be smaller than the smallest resistors or inductor. Correct. That's definitely correct. That will be the definition. So if you have 100K and 3 mega, for sure it will not be. It will be smaller than 100K. Okay. Will be smaller than the smallest resistance that you put in parallel, as Marianne say. Yeah. Okay, so I would like to then do some exercise with you, still to train about these things, because this one again, I should not do this because you should know these things again by your own. But given my experience, you forget stuff. But it seems this year you remember quite well things, except that the derivative part in the top, that is pretty understandable because it's not your fault and it's something that you didn't go in detail in the lab. But let's test you again. So I want to now that you recognize series and parallel between resistance, and I will draw one circuit and you have to tell me if the resistance I'm asked, they are in series or in parallel. Last year I did a Kahoot things about these things. It was pretty fun, but I think I still have. Maybe next time we can do it, or maybe later. Okay, so in this circuit, I draw Rx and Ry. And R, let me also write the source maybe. Let's do like this. Okay. Rx, and Ry in series or in parallel? So please write in the chat so I can understand what's your opinion. Correct. So they are in series. That's great. Because why? Because this voltage source create a current, and this current is flowing, the same current flow through the two resistance. Correct. Let's do something a little more challenging. In this case here. Exactly, things. This and like this. So okay, I just draw this. So Rx and Ry. So Rx and Ry in series or in parallel? Someone saying parallel. Okay, let me see if there is someone other that can answer. Please just answer. So, okay, all agree. I would like to have a feedback also from other. Okay, Vanessa also, great. Parallel, okay. Other. I would like to listen maybe Ivan or Even or Annalene or it's nice to hear your opinion. Is Julian, okay, parallel, okay, maybe sufficient. Okay, this is very nice. As I said before, this is a tricky question. They are not neither in parallel, neither in series. And that's why I told you, you will have trouble to understand actually what is really in parallel and series. The reason is, again, if they are in parallel, they need to have the same voltage. But these two resistors cannot have the same voltage, right? This is the definition of parallel. This is the voltage of VRX. This is the voltage of VRY. You see, the difference is there will be this voltage of difference between the two voltages. So this cannot be in parallel. So the definition of parallel resistance is only if the voltage of VRX and VRY, they are the same. Otherwise, they're not in parallel. So you cannot substitute, you cannot replace Rx and Ry with one resistance here, right? So that's why they are not in parallel. Yeah, this is in some way is a definition, but how to say, the point was this: whenever you have parallel resistance, as I said before, you should be able to replace them with an equivalent resistance, but with the formulas that we say before, right? In this case, you cannot do that because, again, you can try, but again, the circuit that you will obtain will not be equal to this. So you will get different result then. It's a different circuit, right? So again, series resistance are those ones that have the same current, and you can replace the resistance in series with an equivalent resistance, which has the sum of the value of the resistors. Parallel resistors are resistance that have the same voltage, and you can substitute them with a single resistance with the formulas that we discussed before. Okay. As you say, the reason why someone say they're in parallel, because you are thinking, as I think Ole said before, that these one are in parallel branch. That's correct. They are in parallel branch. But the fact that they are in parallel branch doesn't mean they are parallel electrically or they are parallel resistance. Okay. Because again, the definition is that if they are parallel, you can substitute them with an equivalent resistance, which has the formulas that we say before: R1 times R2 divided by R1 plus R2. Okay. So correct. In other words, the components with the same start node and a node, they are in parallel. Yeah. I like to say the same voltage because for me it's easier to remember voltage and current. But again, it's the same. If you want to think about node and loops, is okay. I don't like node and loops. So yeah. But this one is a tricky question made on purpose. Don't think anymore about parallel branch. Think about, if you want, as Ole say, node and loops, or you think of as maybe I do in terms of voltage and current. Okay. This is the definition that we will use in this course. Okay. I will try another. Okay, as you can see, I will do in this course many tricky questions just to tell you. So this because actually I shouldn't tell you, because then you will be more judgy when you listen my question. But that is what you have to do. You have to be critic. Not all the answer they are easy answer. Okay. In this case here, okay, this one I call case B, this I call case C, and this one I call case A. In the case C, are the resistance in series or in parallel? If you want me, I can draw also the voltage source like this. Or neither. Are series, parallel, or neither? This is a question of $1 million. Feel free to ask, to answer on the chat or in the microphone. It doesn't really matter. I need your opinion because Again, I need to understand if you understood these concepts or not. If we are microelectronics, and if we are still have to understand if something is series in parallel, we have to spend the times here. I'm definitely willing to cut out the topic of this course, like maybe don't study MOSFET and so on, if you require that you need to understand series and parallel, because you cannot definitely pass this course without knowing this. I won't do that. If I catch someone that does not know, then I will try to stop it. So okay, so Evan say series, Marianne say parallel, and Lillian say series. Okay, can I have more answer? Again, I ask you to answer because it's for you. If in the future I will catch you, as I told you, that you don't know this difference is now we are just discussing, so I can tell you and why is wrong and we can discuss, but let me know. I can help if I can help in some way. Yeah. Okay, Julian, serious. Vanessa, do you have any opinion? I don't know. Amanda, maybe, if has some opinion. Andreas, what's your opinion? Of course, you will have more difficult to answer if you don't remember very well this concept. So, okay, Andreas say current is the same. So I suppose he say that is in series. Okay, I just want to repeat the question. So I want to know if Rx and Ry are in series or in parallel or neither. Okay. Maybe before I didn't say correctly, but this is what I want to know. So if someone of you, if I said something wrong before, then you are free to change your answer now. But anyway, let's go forward. So the resistance are in series, at least Rx and Ry. Okay, I'm asking just for Rx and Ry. This again because the voltage source create a current. The current is here. Let's call it I0, right? Okay, then there is this node. The current split into part, I1 and I2. Okay, and then the current join again in one current. And what will be this current? Well, it can be, has to be E0, right? Energy and current cannot be destroyed, neither created, as the physics principle. So, or Kirchhoff law current. That's correct. So the current that passes through Rx is I0 too. So you can see that the current in Rx is I0, the current in Ry is I0, so they are in series. Okay, so in theory, in this circuit here, so this circuit here is equivalent to another circuit that I draw like this. They are equivalent. So, and here I put Rx plus Ry. They are identical, okay? I can do that. Although they are far from each other, as you may think, but I can do that because they are in series, okay? This is not magic. This is not tricky. It's not magic tricks. This is theory. Okay, I can do this because they are in series. Okay. Yeah. Okay. So what's the time? 3:53. Yes. Please let me know if someone of you has some trouble to see these things or to understand. I can spend a little more time, try to invent on the moment more exercise if you wish. Otherwise, I will proceed. I think at this point we need to do a break because I will change topic for. Okay, also the next hour in theory should be under reasoning, okay? But as you see, during my Forelesning, I like to do some, at least for the electrical part, I like to do exercise while I'm doing Forelesning. So it's kind of mixed, okay? So I will proceed with the theory and try to do some exercise with you while I'm going forward. So it's kind of mixed on the reasoning and Forelesning, okay? At least this is what we do on Tuesday. So I want to do the break now, so I can start with a new topic as soon as we finish the break, okay? So take maybe 10 minutes of break, yeah. Yeah, even less if you wish. If you already did everything, you can do less. For me, is I know. I mean, a break is very useful, but I know our time is very limited. I remember last year, I was last year I was saying, okay, after the minutes, you just come back, and all the students, no, one more. So, you know, I think it's okay. It doesn't matter. But just because the time is very short, so that's why. Slowly and I don't know. Give me also your feedback if the lecture with the exercise like this in Zoom it work. Usually I do this exercise on the whiteboard in the class, and I can see the face of the students when they ask something that they don't know, so I can easier understand that. But now is a little is a little more challenging. But again, yes, definitely. If as we said, maybe these 2 weeks will be like that. And then if nothing changed, then definitely we can start to do this one physically. And that's good. That's good that the whole class is there, and that is very good. So let's see. Let's see. But yeah, I hope that with the pad, I kind of like still have the way to show you things on practical. So I like to solve things and show you how to solve them. Okay, so I suppose we have to start again. If any one of you has some question about what we have we have discussed until now, then feel free to ask. Otherwise, I will continue. Remember that this is just the third probably lecture, and I will provide you more and more and more information. If you lose something, then it's hard. It's very hard. Okay, let's continue. The next topic is DC electrical circuit. We need to understand, at least we need to remember how to solve electrical circuit, which are powered by a constant power source. Okay, in my in my examples, I will consider a battery. So I will use the symbol for a battery, so everyone know that the battery generates constant voltage. But again, it can be also, I can also use the other symbol with the circle, but I just use the symbol of battery because again, it's quite obvious, I think. Okay, the first things you have to remember when you solve circuit or analyze, regardless if it's constant voltage of or sinusoidal signals or whatever, is the two most important law, which are the Kirchhoff law voltage and the Kirchhoff law current. I think I'm not sure actually if I'm writing correctly or wrong. Maybe all I said before should be KCL, but it doesn't really matter. So it's a Kirchhoff. I even don't remember this Kirchhoff name, if I wrote it correct or not. Kirchhoff law voltage and Kirchhoff. There should be an H, I think, somewhere. Law current. Okay, and so the Kirchhoff law voltage say that the algebraic sum of the voltages in a loop of an electric circuit must be equal to 0. This is the Kirchhoff law voltage. I think Jorgen for sure explained it in other words. There are many definitions. This is the definition that I like it more. You can use your own definition. It doesn't really matter. But again, the important is you get the correct answer. As I said before, the definition I give for resistance in parallel and series are one way to express that definition. There are many other ways, but that is the way that give me always the right answer. That's why I give you these definitions. Yeah, maybe it's KVL and KCL. Yeah, but yeah. So okay, then let's write it KVL and KCL. So like this. So just to be correct. And so again, the Kirchhoff flow voltage say that the algebraic sum of the voltages in a loop of an electrical circuit must be equal to 0. So let's start with a simple exercise to understand, again, to review the Kirchhoff flow voltage very fast, at least a simple, my point of view of the Kirchhoff flow voltage. So we have a battery, which I indicate with Vs. This is the positive terminal. These are 1, these are 2. Usually you have to draw the current. Again, when you draw the current is always up to you to decide what direction it is, okay? So in my case, in most of the case, it makes sense to assume that the current come out from the signal generator or power supply. So the current in this way will do like this. I call it I. And as you can see here, there is a loop, which is this one here. This is a loop. So now the sum of the voltage in this loop should be 0. This is what the algebraic sum of the voltage in this loop should be 0. The way that I solve usually this exercise is to start to draw in the circuit the voltage over the resistance and over the different components. I know that most of you like to use this probably way to do like this. I don't like this. I won't use this because I prefer the other one with the arrow. You can use whatever you want, but in my explanation, I will use this, where the tip of the arrow indicate the positive terminal of the voltage that you're considering, and the other end is the negative. So this is VR2, okay? I will draw just arrow. So this is VR1. So you understand this is positive, this is negative. Only this time I put the positive negative sign. In the future, I won't put it. And this is VS, which is already written there. Okay, so how do I find the voltage in the loop? So of course I have to start in one point. So I write this one is my point 0. Then I move. I go to the point 1. Then I move over the resistance R1. I go to the point 2. Then I move through the resistance R2. This is the point 3. And then I go back to the point 0. So again, I go from 0 to 1 to 2 to 3, and then I go back to 0. Okay, this is the path that I do to that goes through the loop. Okay, so I start from 0 and I go to 1. Now there is a component in between 0 and 1, which is Vs, and you can see if I go, think about yourself, which is in 0, and then you want to go to 1, right? You can see that the arrow over Vs go in the same direction that you're going, okay? From 0 to 1, the arrow of Vs, this arrow here, is in the same direction where we are going. We are going from 0 to 1. Therefore, I have to write Vs with a positive sign. If the arrow is against your movement, then is negative sign. So, okay, so now I'm in 1. This is why I like to use the arrow. I'm in 1 and I want to go in 2, okay? You can see if I go to 1 to 2, VR1 is an arrow which is in the opposite direction where I'm going. So then I have to write minus VR1. Then I'm in point 2. I'm going to point 3. The arrow of VR2 is opposite in the direction where I'm going, so minus VR2. And finally, I'm going to point 3 to point 0, but there is no component in between, and there is no arrow, right? There is just the current, but there is no drop voltage there. There is no arrow. So I can go between 3 and 0 without writing anything on the equation because there is nothing, no voltage in between. And once I arrive to 0, I close the loop. So the loop is finished. And I know that the algebraic sum of this voltage should be 0. And that's it. So this is how to use the KLV from my point of view. If I want, for example, find VR1, then I bring this one in the other direction and become VR1 is equal Vs minus VR2, right? And how much is, because the only thing I know is the value of the resistance and the voltage source, right? So I don't know, still don't know how much is VR2, right? So I cannot solve this equation. Let me put some number here. So right here, 1 and 2. So here I know just Vs and the value of the resistance because it's the one that I use for building the circuit, right? But VR2, I don't know. So I have to continue to solve this equation to understand how much is VR1. So VR2 can be written as the current multiplied for R2. This is from the Ohm's law. But also the current here, I don't know, because it's something that derived from the circuit, right? How much is the current? Well, the current is given by the voltage divided by the sum of the resistance in the circuit. So Vs, let me write it here. So here, the current I don't know, but I know that this is Vs divided by R1 plus R2, because R1 and R2 are in series, right? And so the result is equal Vs minus Vs divided by R1 plus R2, all multiplied by R2, which also means Vs taking common 1 minus R2 divided by R1 plus R2. This is equal to Vs multiplied for R1 plus R2 minus R1 divided by R1 plus R2. R1 and R1 go away, and the result is equal Vs multiplied for R2 divided by R1 plus R2. Okay, and now I can stop. Why I can stop here? Because I know Vs, because it's the battery that I place on the circuit, and I know also R2 and R1, which are the resistor I put in the circuit, right? It's me that decide what is the value of these components. So here I can stop. So I have all the I have a formulas where I can put all the value that I know eventually and calculate VR1. Yes, I can write the differently, definitely. I will try. That's good. So let me know if my R is very ugly. I will try to improve the R here. Let me see if I hope this is better. Let me change it here so it's clear. Yeah, this is the spending dollar. This I suppose is okay. The voltage divider, yes. Yeah, my R is very ugly. But here, here, and here. Yeah, so I try to modify all the R. I hope that this now is more understandable. Yeah, so this is the only probably times I will show this calculation like this for two resistance. This is, of course, as all I say, is spending the LR. And I'm definitely expecting you that you know these formulas, final formulas here, and you don't have to go through all of this calculation every time. These are formulas that you will use so much, so be very familiar with it, and in some way it will remain in your head as much as you train. So if you start to calculate this one every time that you have a spending dollar, then we finish. We need another course. Okay. So this one is for the KVL, yeah. And another things I want to emphasize on this exercise, so I think every one of you understood what I did here. Another thing is this. This one derived from what we did in the digital part. This is VS, this is R1, and this is R2. As same as we did in digital part, especially when we have only a single power supply. So in this case, there is only one battery, right? We are free, or you can find circuit drawn like this. And you know why now, I hope. Why I draw this back here? I wonder what does it mean. I think there is someone that study calligraphy and they know what does it mean when you write in some different things. Okay, anyway. The two circuits I draw, they are equivalent. In the right side, I use the ground symbol that you know, which is the triangle. And in the left side is just what you draw usually in electriske kretser and so on. So it's very common in electronic circuit that we use the ground symbol, okay? So don't be surprised if you see that. Actually, this circuit can be even drawn in another way, which is the following, which is actually the one that we will use very often in this circuit. And you already know what are these kind of like symbol, right? I hope. So these three ways to draw the circuit, they are equivalent and identical, okay? So be familiar with this way to draw the circuit. Okay, finally, let's go to talk a little about circuit, DC circuit, when there are capacitance inductance, okay? These are typical tricky questions. I will start with an example to understand what you know, what you don't know, and then I will try to give you the rule. So this is an example. Okay, and then I draw this circuit here. Try to do it with me. Someone say, oh my God, it's very complicated this. Let me see, R1, R2. I definitely, sorry if my R is very ugly, I try as much as I can. R4, L. Okay, so how much is, I want that now you answer the question, how much is the voltage at the output of the circuit? We have a battery, we have an inductor, and we have also some resistance. I want that you calculate for me, find the formulas for the output voltage. I give you probably 15, let's say 30 seconds, yes. And because this is the time that you have to take for solving this exercise. And so if you know the answer, then write it down on the chat. And unfortunately for you, I'm not kidding. This is the time that you actually have to use for this kind of circuit. I know that probably when I say 30 seconds, some of you have started to laugh or whatever, say this is crazy, but this is what should be. This course is it's like that. You are, yeah. Okay, well, let's say R1 plus R2 parallel L plus R3 parallel R4. Okay. I would like to have more answer. Vanessa says 0. And then more answer, please. So for the moment, we have two different answers. I should have put a timer here, but that would be great. Maybe next time. Next time. But please answer. Whatever you have in your mind, just give an answer. Or say, I agree with Ole, or I agree with Vanessa. I'm also asking this question to show that what is your level, you understand? So I can maybe focus more, spend more my times in the topic that you don't know. Okay, Andrea say that. Aside say okay. Maybe something from Lilian or I don't know, Annaline or Julian. What do you think? TikTok. Okay. I think I will tell you the answer, the magic answer. The magic answer is 0, as Vanessa said. Again, this is why I also say this is 30-second question, because there is not much to think here. Probably you just don't remember. I hope that Jorgen went through these things. Okay, but anyway, the reason is because whenever you work in DC, whenever you work with constant voltage, the inductance is just a wire. It's just a piece of wire. So in this case, and I will prove you also why, but I will just show you the answer here. In this case, what I will do is just substitute the coil with a wire here. So you understand that this part here is not powered at all, because let's say that the current is going here, then there is a node in my split, right? Part go in R2 and part go in the short circuit, and then it's going back, right? And then it's doing like this. But no current can go in R3 and R4. Actually, neither current can go in R2 also, because the short circuit, this wire here that they draw, has practical resistance 0. Remember that the current won't think about you are an electron, you always want to pass through the path that has less resistance, okay? So yeah, of course, if the conductor is an ideal component, yes, let's say that, okay, so let's assume that is an ideal component for the moment, because it's the simplest way. And that's correct, good point. And in this case, so this piece of wire that I draw here has resistance 0 if it's an ideal component. Therefore, the current want to flow just through that piece of wire. And because it's the smallest resistance he can find on his path. And there is no current through R2, neither current through R3, neither current through R4. If there is no current through R4, and you remember that VR4 for the Ohm's law is R4 times I, and this one is 0, VR4 is 0, but VR4 is equal V out. So then this means that V0 is equal V out, okay? So this is something that at least ideally work like that. It will work also in real life, because as I said before, this piece of wire, ideal piece of wire in the real life will have a certain resistance, but again, will be a very, very small resistance. I don't know, maybe 1 ohm or 0.5 ohm, something like that, even less if the wire is very good, okay? So in theory, when you solve a circuit at the very beginning, you can assume that is an ideal wire. Then if there is some strange behavior in the circuit, you can start to add giving some more thought about it and try to treat cables also as real resistance, okay? But at the very beginning, think everything ideally, okay? This is what we will go do now, but later on in the course, I will start to tell you, now we have to start to think in the real world. Okay, so this is an exercise that is very important, and you have to understand these things. Okay, so this is, I wanted to check, so what you remember about this inductance and capacitance. So the point is this: any inductance that work in DC with constant voltages or constant current. So if the circuit is powered by constant voltage and constant power, then any coil inductance behave like a short circuit, okay? Short circuit. Or just a wire, okay? Remember, is a synonym, or ideal. Let me write ideal wire. Any capacitance instead in DC work as an open circuit. Okay, so here open circuit. Correct. But why is that? Can I prove it? Can you prove it? Of course, we are going to prove everything in this course. There is nothing that will be left unanswered. I don't give you rules just for remembering. Let's try to look. And here, to answer to your question, I'm going to use the constitutive equation of these two components. That's why I told you these are very, very important. Let's start from the capacitance. You know that the constitutive equation for the capacitance is equal to IC is equal C dVc over the T. And let me see here, what is the circuit here? Yes. Yes, so let's assume in this circuit again, okay, here we use an inductor. Maybe we start from the inductor. Yeah, let's start with the inductor. So you remember, you relate better to the example. So the inductor has voltage VL is equal L times dL dt. Okay. So when you use constant voltage as a power supply, of course, all the current and all the voltage must be constant, right? Because there is no way that the voltage here over a resistance in this example here, right? There is no sense that you find a sinusoidal voltage. Where does it come from? It's impossible, right? But because you use a battery which produces a constant voltage, it makes sense to expect on the circuit that all the voltage and currents are constant, right? If that is the case, then I'm expecting that the current, right, in the inductance will be also constant. I don't need to know how much it is, but it must be constant anyway. If the constant, the current is constant here, the derivative of a constant is zero. So this means that the voltage across the inductance must be zero. It must be that. And you remember that when we talk about digital part, there is one component which is the only component which have like a short circuit or a closed switch because the voltage across the inductor is zero. Okay. In the same way, I'm going to prove why the capacitance is an open circuit in DC. So here is the capacitance, and in DC we have IC is equal C dVc over dt. Now, as I said before, the point is that if in the circuit we have a power source which is constant, it makes sense that in the circuit every quantities are constant. So let's say we have a circuit, we don't know which it is, doesn't really matter, and we have one capacitance in this circuit, okay? So it makes sense to expect that the voltage over this capacitance will be constant. This means that the, the derivative here will be zero. This means that the current through the capacitance is zero. But you already know from the digital part we did in the previous lecture that there is a component that has current zero, which is an open switch or open circuit. In fact, in an open circuit or an open switch cannot flow current, right? It cannot flow. There is no way that the current pass through. So the capacitance behave identically to an open switch or an open circuit. Okay, so this is very important. Please let me know if you did not understand my explanation. It's a very important point. Let's have a look about another example. Okay, all I say with, what do you mean with constant? When I say constant, I mean that the value, which could be voltage or current, does not change in time, okay? So for example, in this exercise here, you see that the power source, which I call Vs, which is the battery, generate a constant voltage, right? In this case, is the voltage generated is constant. So this means that all the quantities, electrical quantities in the circuit, voltage, current, whatever, must be constant. So constant in time. They don't change in time. They always remain the same. If you calculate VR1, and VR1 is you calculate 5 volt, will not change, will be always 5 volt, regardless in which moment of time you measure, okay? So this is what I mean with the constant. And let's do another example. Also here, I give you probably 15 seconds to solve this circuit. Try to do it with me. This is something an engineer should know, an electronic engineer, at least someone that come out from my course should know. Then I don't know the other course, but I mean, if I was the responsible electricity Kretzer, this is something I definitely would go through. Okay, someone say if Lilian said that if the IL change over time. Well, whenever we are going to, this is a good question, and will be introduced probably in the next lecture. What you say is actually correct in the sense that whenever you turn on the power supply on your circuit, inductor and capacitance need a little time to charge. So the voltage over the capacitance will increase exponentially, and also the current in the inductance. That's correct. So it needs a little time. However, what we are doing is called DC analysis, okay? And this is a good point that you brought out, because DC analysis means that we analyze the circuit, so we are interested in the circuit when the circuit has reached the steady state. So in other words, we are just evaluating the circuit when t go to infinity. So after long time, okay? So this means that if we evaluate the circuit, if we are analyzing the circuit after long time, we cannot see discharging and discharging, the charge and the discharge of this component, okay? We just see the behavior of this component after that charge and discharge, okay? So what I'm saying is that the capacitance will behave as a open circuit after a lot of time that this circuit here, for example, I draw, it has been turned on. And the same for the inductance. The inductance work as a wire after that this circuit here, for example, has been turned on. Yes, so you can see the behavior of charging and discharging of the capacitance just if the power source of the signal you apply change in time. In this case, the power source is constant, so the behavior of the capacitance and the inductance when the power source is constant after a lot of time is open circuit and short circuit, okay? So this is something indeed that maybe I should remark a little more. So in this circuit, what you are interested is the behavior of the circuit after a lot of time, okay? So you are analyzing the circuit after a lot of time. And this is actually what most of the time happen in this circuit, because think about you're in the lab, right? This VS here that I draw in this example is your battery or your power supply, right? So then you turn on the power supply, right? And then you go to measure the voltage at the output of this circuit. Now, if the capacitance and the inductance are a small value, you will never be able to see the charge and discharge of this capacitor inductance when you go with your voltmeter or oscilloscope, because you should be so fast or to see with your eyes or to go with voltmeter to point in the output voltage to see this variation, that it cannot be done. So what you actually see, what you measure usually is after 1 to 3 seconds that the circuit has been turned on. And that is the DC value, okay? So this is why it's important to emphasize these things. I hope that this is clear. If it's not, I will repeat it again, so let me know. Okay, so please solve this example. I give you 10, 15 seconds to solve this. Give me your answer in the chat, and then I will give you the answer. try to answer as much as you can. I hope that if you understood what I said until now, then you should be able to solve this circuit. Okay, Julian says 0, Lillian says 0, Ole says 0 volt because the current is 0. Okay, here a comment on the comment of Ole is whenever you say current, is always good to specify which current, but in your case, maybe it could have been something kind of obvious because you probably mean the current through the resistance R3. But it's not good to write I itself. Maybe you can write IR3 or the current through the R3. It's just a comment, just a detail, you know. As engineer, many times you are picky, so you have to bear with me if sometimes I say this this detail. Okay, but anyway, the result is 0. And the reason is because we have to substitute the capacitance with an open circuit because in DC it behaves like an open circuit, and we substitute the inductance with a short circuit. But again, because here there is an open circuit, cannot flow any current, so there cannot be any current neither in the other part of the circuit, so this must be 0. Okay, so this is pretty straightforward. I should have lived like that. Let me do A equals 0. Yeah. Okay. So anyway, you can find it also in the slide. So yeah. Okay. So I hope that this is clear. Soon probably we have to stop. I was hoping to do more things, but yeah, I will maybe stop with the next. Emily and Norton will do next time. Yes. So the next topic I want to go through is voltage divider and current divider. Divider and feel free to ask questions if you have. Okay, so we saw before the voltage divider. The simplest way to do a voltage divider is this one here, R1 and R2 Vs. Then this is the voltage I want to calculate, VR2. You should dream about these formulas, which is simply Vs times R2 divided by 1 times R2. So you should not spend any time to think about calculate the current, calculate whatever. No, you should know these things very well. So let's see what is the value of a voltage divider when we have many resistance. Enjoy like this. So in this case, there are n resistance. So this is, at least you can see the general rule. This is called Ri. This is R1. So if I want to, for example, measure the voltage over Ri, so this is what I want to calculate. This is equal to the power supply voltage Vs, or the signal, multiply for the resistance over which I want to measure the voltage, divide by the total resistance of the resistance in series. So in this case, it's just E to 1 to N RK. Let's call it this one K. So this is the formulas. Okay. Correct. Good. So let's do the current divider. I think you are less familiar with the current divider, probably use more the spinning Deller. If any one of you know the answer, just write it on the chat so I can see who knows, who doesn't know. We want to calculate IR2, for example. Remove here. Okay, so IR2 is equal to IS. Just to R1 divided by R2. I just show you the full procedure. Divided by R2. Okay, here I want to show you, because also for me sometimes these formulas I don't remember, but it's easy to remember. I mean, it's easy to derive it, right? And I show you with this method how did I derive. What did I do is this. So I substitute these two resistance, right, with an equivalent parallel, which is this term here. And then I know that the current IS pass through this parallel resistance, right? Which means that the voltage across this parallel resistance is just IS times the parallel, okay? So now I know the voltage here, which is this one here. I call it VR2. And then I divide for R2. And then we give me the formulas for the current in R2, which is just nothing else than IS times R1 divided by R1 plus R2. So in other words, if you want to find the current on a resistance, you have to take the source, which is IS in this case, multiply for the other resistance in parallel, and then divide for the sum of the resistance. Let's see, for example, another example with the general case. So we have R1, then we have RE, and then we have Rn. So they are N resistors in parallel. And I want to know how much is the current in the resistance Re. Is IS. So the formula is equal to IRE. So I have to do the, IS, which is the power source. And then I want to use just the trick, the question, the formulas that I used before, because it's easy to generalize. So I use the same method that I use here. So I multiply for R1 parallel R2 parallel blah, 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 parallel Rn, which is the same things that I did here, right? Is the formulas for the parallel. Divide by Re. That's the general formulas. I wrote it a little more in compact way. There are also other way to write it. Let me remove this one. Okay, but again, in this parallel here, remember that is excluded Re. Okay, no, there is no Re. Sorry, it's not excluded. Let's do an exercise very fast, and I think probably will be one on the last. Let's say that we have 10 volt. For this question, I give you also 10 seconds. I want to find the voltage here, VR2. Please, when we do this numerical exercise, try not to use the calculator. Definitely. I definitely suggest. As I told you, the brain is your first calculator. And most of the time in my exercise, you don't need. Okay, 10 seconds from now. How much is the voltage VR2? This you should answer with your blind eyes, you know. At least at the end of this course, I hope you will do that. This is what is my purpose. So if you don't understand, actually, the top is 1K, this one is 2K, and the bottom is 7K, okay? Again, these are things that, I mean, this example that I'm bringing you I just want to show you that actually most of the exercise I'm doing is based on logic, okay? It's something you have to start to use more your logic. It's not like a mechanical thing like you do in Elektriske or Mathematik, that you just use the formulas, put the number. No, this is definitely, if you think that that is the course, or if you think that that electronic engineer means, then you're totally wrong. The engineer hate using formulas if he can just use the logic to understand what is the result. Here again, okay, there is no need to any calculation because 10 volt is the power supply. Most of you got the correct answer. That's very good. 10 volt is the power supply. As you can see, these are 3 resistors in series. The total resistance is 10 kilo ohm, which means that the current is 1 milliampere. Multiply for 2K is 2 volt. So it's not, there is no need of anything. So in this case, you're actually lucky because the total resistance, if you see, is precisely equal to 10. So practically the output voltage is equal to the value of the resistance without the K, okay? So this should have been very straightforward. Let's see another example. So the answer here is 2 volt. Then we do like this. This is still 10 volt. I want to find the voltage here. Tier 1. This one is 3K, 3K, and 3K. 10 seconds from now. I'm sure some of you has used the calculator. I'm quite sure. This is anyway something that okay, someone say approximately 3 volt. 3.3 Marianne. Okay, but yeah, I think correct. So most of you got it right. So I want just point out a few things. The question of Ole is, the answer is Ole is good. In this case, if I was in you, maybe I would add 1 digit after the comma as Marianne did. So I like that 3.3, but definitely the answer of Ole is definitely good also. The answer of SID, I said before, I definitely would like to avoid to see 3.3333333 because anyway, in the practical world, it doesn't make any sense. And I can tell you why. This is something, but it's good that you make me pointed out this. Anyway, we are all learning here. The reason is this. Think about what I said before. The resistance that you're going to use in the lab, and anyway, they are not precise 3 kilo ohm, for example. They have a tolerance, right? So in the end, the current that you're going to measure will not be 3.33333. It's impossible because the resistance in first of all is not precisely 3K. So that's why in electronic engineering it's not very useful to put many digits, and you have to learn when to stop. Okay. Yeah. So that's good answer from Saidi, but again, just please take that in mind. So then it will be much better to show less digit. Yeah. Good. Let me see. Let's try to do maybe a current divider. So this is A, this is B. The answer yes was approximately 3.3 volt. And when you say approximately, I hope you know the symbol is like this. Number, this is the C. This is IS. This is 1K. This is 1K. This is 1 ampere. How much is the current that I call IX? Answer to your, that's great, 0.5. Someone answer, oh, I didn't know that you can interact actually there. That's great. Yeah, so then I think there is no need to wait, but let's great, yes, it's 0.5. Yes, correct. Here, to be honest, use your logic also, right? So the resistance are the same. And as I say before, the current want to pass where there is less resistance. But then when the current starts, we'll find two paths which have the same resistance. So for sure, the current will say, okay, they are the same resistance, then what I do? I split myself. So it split itself in the same way, and then it go back. So it makes sense in this case that here there is 0.5 and here there is 0.5. So no calculation here were needed here. It's just a logic thing that you have to think about. Okay, so I think we'll stop here because then we have to do some Thevenin and Norton, which are the most important concepts. We have to go to the AC analysis and then the transient analysis, which is the one that I don't remember who was it. Maybe Vanessa was mentioning before, or Amanda, and about the transient, the charge and discharge of capacitance and inductance. So be ready that the next time we're going to use derivative to solve that things. Some of you just use the formulas of the exponential. Again, I don't like to remember things, so I definitely not encourage to do like that, because it happened many times that if you write the formulas for your exam or you read it not correctly, then you do a mistake. So at least this, I think, is what I think. My philosophy is almost never rely on your memory. Rely on your logic. Try to derive what you can derive. I like electronic for this reason. I don't have to remember almost anything. I derive everything that I need. So if you know the four, 5 rules like Ohm's law, KLV, and KLC, it's just a few rules that you have to know. After that, you can derive whatever you want by your logic. Remember, electronic is like this. If you expect something like give me a method to solve the circuit, this is not the course for you. Furthermore, remember that this I want to emphasize before to close the lecture. The solution that I will give, or the procedure that I will give you in the course, they are a possible way to solve the circuit. In electronic, there is no a single answer. Okay, so you may have another procedure. I use another procedure. So the important the result is correct.
Luca,
yeah.
Could you upload this OneNote sheet?
Yes, I will upload that. Yes, I will upload in maybe in the Forelesning notator part. So you will find both the PPT and maybe also these notes. So you have both.
Okay, thank you.
Yeah, you're welcome. Okay, so but I think for now is done. So let's prepare for going to the lab. Let me give